Welcome back, guys. This is the last lesson of calculus that you will have. It's very sad, and it's not even calculus based. It is mostly just about a different coordinate system that you've not had a ton of exposure to called polar coordinates. It's another way to look at graphing things instead of XY coordinates. You can have R theta coordinates, and basically you can use this, and it's very handy. It can make a lot of cool looking graphs and stuff like that, but mostly why I want to teach you this is not because it makes a bunch of cute little figures and stuff like that, because this is very useful when doing calculus on regions that are circular, and anything involving circles, this would be something great to know. Now it's beyond that too, but we're going to talk about all that and get into it, so here we go. Number one, warm up today, though, let's review things from last time, which were about slope fields and equilibrium solutions. So for the given differential equations, find all equilibrium points, classify them as stable, unstable, or semi-stable. So here's a bunch of differential equations, and we're going to see what all of them are, analyze them one at a time. Here we go. So here is what y prime is, in other words, dy over dx. Remember, equilibrium solutions happen when the slope is equal to 0. So if I set this equation equal to 0, all that's left are y's, and I can factor that and easily figure out what makes equal to 0 are 2 and 4. So if you go plot this slope field, and this is Desmos right here, this is what you kind of see on it, and you go plug in this for your slope field, this is what you're graphing, y squared minus 6y plus 8, this is what you'd see. And notice that at 2, right here, this black line, is a solid horizontal line. Horizontal lines that are slope is 0 and just staying that the whole way, that's an equilibrium solution. So there it is at 2, one of them. And you see up here, there's also some dashed purple lines here, and that's at where y is 4, which is the other equilibrium solution. So you can know there's equilibrium solutions at 2 and at 4 right there. Now, are they stable, unstable, or semi-stable? Well, let's take a look at that. One thing you could do is a sign chart on your derivative. So this is a axis representing your derivative. And since your derivative depends on y's, we're not going to do it with x this and x that. We're going to do it with y's, up and down stuff this time. If you did a sign chart on this, this is a quadratic that opens upwards from the traditional algebra 2 standpoint. So it goes plus, minus, plus. And that is what the sign chart would do here. Now remember, the sign chart represents the derivative. So for y's that are less than 2, which is anything below this black line, the slopes are positive. And you can see over here that these slopes are all kind of going up. They're almost vertical. They're not really vertical, but even when they're slanted, they're going upwards. So it's a positive slope there. You see between 2 and 4, the sign chart says the slope is going to be negative. And between the black line and the kind of purple line here, where it's 2 and 4, you can see that these red lines here are slanted downwards. And then anything above y equals 4, the slope is positive. So again, above the purple line, you kind of see things with positive slopes right here. And that's where this kind of a rough sketch of this slope field would look like. Now, are they stable, semi-stable, or unstable? Well, let's see. How about the one at y equals, let's start with just going in numerical order, y equals 2. So down here, the black line. Here, I see that solutions around it are getting closer to it. This below it is curving towards it, and above it is curving down towards it. So since things are getting closer to it, solutions are approaching this. This is a stable equilibrium point. So y equals 2 is stable. On the other hand, if you look at y equals 4, you see that below it, the lines are going away from it, and above it, the lines are going away from it. So things are diverging away from this one on both sides. So this would be an example of an unstable equilibrium solution. So y equals 2 is a stable equilibrium solution, and y equals 4 is an unstable equilibrium solution for this. Number 2, same kind of deal. The reason I put this divide by 500 here is, like I said before, if you graph things in Desmos and they're too steep, they almost look like vertical lines, you might want to scale things down, take your slopes down by like a factor of 100 or 500 or whatever you happen to do. And when I finally did this original problem and divided by 500, I got a picture that kind of looked like something I would look for. Now, again, equilibrium solutions are where y prime is 0. So y prime is already factored for you. Looks like at -8, 0 and 3, that is what makes things equal to 0. So those are my equilibrium solutions. Y equals -8, y equals 0, and y equals 3. Down here, this blue line, this horizontal blue line is y equals -8. It's flat, good. At y equals 0, you see this kind of like a purple thing here, but it is flat. And at y equals 3, you have this red bunch of lines which are also flat. So those are equilibrium solutions. Their slopes are 0, and they're just horizontal lines. No big deal. So if those are the zeros of this thing, a sign chart would kind of give me a feel for what this slope field will look like without even graphing it. So if you go graph y prime, okay, and you put down all your zeros, -8, 0, and 3, and you plug in test points into this equation for y prime like you would any other sign chart, you would have got positive, negative, negative, positive. It does not change at y equals 0 because that's a double root right there. It's a double 0, so it does not change signs right there. The multiplicity is even if you want to go with that. So what's that mean? Below, remember this represents what's going on vertically, okay? Because this is all y stuff here. So below -8, the slope is positive. And if you look below the blue line, there's red ones and there's black ones down here have positive slopes. Okay, cool. Between -8 and 0, I should have negative slopes. So between -8 and 0 right here, you see all the lines in here, to some extent, they are sloping downwards. And between 0 and 3, it also says it's negative. So between here, 0 and 3, and you can see these black lines is barely kind of tilting down a little bit, but they have negative slopes. And then above at 3, I see some positive, so the slope should be positive. So above this red line, all these things have positive slopes, and they go up. So the sign, or excuse me, not the sign chart, but the slope field that I graphed on Desmos very much backs up my analysis by hand. Okay, oh, the equilibrium solutions are at 0. There they are. I can see it's increasing here, decreasing, decreasing, increasing as I go up and down along the y-axis, and it kind of matches that. So let's analyze each one now and see if they are stable, unstable, or semi-stable. Here we go. Let's start with y equals -8 at the bottom. Down here, you see on either side of it, it's converging towards it. Above it, things are going down, and below it, things are going up. So things are converging to it. So y equals -8 is a stable equilibrium solution. How about y equals 0? Well, here's the blue one right here. Or these purple lines, it's kind of hard to see because it's blended into the axis. But below it, things are curving down away from it. And above it, things are curving also down kind of towards it. So if one side is approaching it and the other side is going away from it, well, it's kind of like a mix of stable and unstable. It's semi-stable. So y equals 0, it's a semi-stable equilibrium solution. And then lastly, up at y equals 3, you can see that below it, things are going away from it. And above it, things are also going away from it. So this would be an unstable equilibrium solution on number 2. Number 3, same kind of deal. Now this one, x is a function of t, okay? So it's the same idea as different letters, okay? Don't always freak out when they give you different letters, but this one, the variable is y is a function of t, if x is a function of t, so the fact that it's still written in terms of x's means it's still written in terms of the function, and that if I can use the same analysis as before. So again, equilibrium solutions happen when the derivative is 0, x prime is 0. That happens at 0 and at -7. So -7 and 0 on my sign chart. This is x's. X is up and down this time. T is back and forth. So x is the dependent variable and t is the independent variable. So this is still vertical things that we're talking about. If you did a sign chart below -7, you plugged it into this thing right here, you get a negative out. If you plugged in a number between -7 and 0, you would still get a negative out. And for x is more than 0, you get out something positive. So let's see if that's reflected on our little slope field right here. Below -7, well, here's -7. Oh, there's the equilibrium solution. Great. Below it, the slopes are kind of hard to tell, but you can kind of tell they're slightly slanting downward. So they do have negative slopes. Above the equilibrium solution of -7, you see that the slopes are positive there. Between +7 and 0. Oh man, I did this analysis wrong. Oh, my sign chart's wrong. You know what it should be. You know what it should be. Tell me what I did wrong. Take a look at this. What did I do wrong with the sign chart? If you plug in something between -7 and 0, say, I don't know, -1, That's positive, and that's positive. So it should be a positive inside of here. My bad on that. And look, the slope field helped me catch that mistake. It is, in fact, positive between -7 and 0. So it's upward there. And if that's positive, let's see, on this side, guess what? It is still positive. That one is correct. So, and you do see over here, the slopes are all pointing upward. So it messed up my sign chart, and that messed up my interpretation. But that's why you kind of want to graph things on Desmos and your calculator and have some kind of analytical way to figure it out. Like everything else, you want the graph to back up your work and your work to back up your graph. And if one of them is saying something different, you analyze it wrong or you plug something in wrong when you calculate it. In this case, I analyzed something wrong. So this middle part of the sign chart should be positives there. Whoops. But anyway, looking at these two equilibrium solutions at -7 and 0, where you see horizontal lines right there, below -7, it's going away from it. It's got negative slopes. And then above it is positive slopes and going away from it also. So at -7, since it's going away on both sides, that would be an unstable equilibrium solution. At x equals 0, you see that on one side it's getting closer to that solution, but on this other side it's going away from it. So one side's going away and one side's going towards. That's called a semi-stable equilibrium solution right there. All right, moving right along. How about this guy? X prime is x times this thingy over 10. And if you factored that, that'd be x times x minus 4 squared over 10. Again, the over 10 is there to scale it, so it kind of looks like this. And what makes that 0 are 0 and 4. So 0 and 4 are going to be my equilibrium solutions. And you see at 0, it's a horizontal line right there. At 4, it's also a horizontal line. Those are equilibrium solutions. And I'll see if I did my sign chart correctly this time. Plugging in something negative over here does, in fact, give me a negative out. So for things less than 0, I should be having a negative slope. If you look at below 0, then you see the slopes are kind of negative downwards. Check. How between 0 and 4? Or in my sign chart, if you plug something in there, you would get out a positive. And between 0 and 4, you see the slopes are all little positive things there. So that worked out great. Above 4, it still says it's positive. So above 4, here's 4 above it. Yes, the slopes are still positive. Okay, so everything on my slope field is matching everything in my analysis. Everything's cool, good to know. If you haven't noticed, things don't change sign on a sign chart when you have an even multiplicity. So since there's a 0 at 4 with a multiplicity of 2, it's one of those things that would bounce on a graph and not change sign. So that's why it's positive right there. But let's classify these equilibrium solutions. At 0, let's see here. On one side, it's going away. On the other side, it's going away, so it's unstable. At x equals 0 is an unstable equilibrium solution. For 4, on one side, it's going towards it. On the other side, it's going away from it. So at 4, it's a semi-stable equilibrium solution there, too. And that's your answer for number 4, and that kind of concludes that. LGs today, learn about polar coordinates and for use in higher level courses, and that'll be pretty much it. This is an algebra-based thing for the most part today, just graph, more of like a pre-calc algebra kind of lesson. But it's something good to know, and we'll calc it up just a tad, and I'll explain you how you would do that. Okay. All right, things are coming due, guys. Extra credit is due tomorrow. Notebook check, you all got 3 points for that, 50 out of 50, so you're good on that. So basically, touch up any extra credit you want to turn in, and there's one more assignment, 9.1, that's the last one. Let's shoot for that being due Thursday. If you want to have it turned in by Friday, I will look the other way, but I want everything for this course completely wrapped up. Grade book on my end, grading on my end, homework turned in from you guys, everything. I want it all done by Friday. So the 8th is the cutoff day and the last day. I want to get grades in the Neosho after that's done. And I want you guys to go focus on other classes that you need to wrap up for the rest of the semester. And this is a college class, so college is about out at that time anyway, so it's fair that this is all over. All right, so that's all you got to worry about. Look at the slide. That's it. And once you're done with homework 9.1, you are done with the course, and you may turn in your textbook to Mr. Adams or whatever the administration wants to do. They'll be in contact with you about how it's going to work. That's it. Make sure your textbooks get back. When there's things in, you're good. So it's sweet. And if you've been turning in all your work, regardless of how bad or good it's been going, well, this is a college class, so I'll give you a little leeway. I'll be a little nice to you, but I can't just fudge the grades too much. You kind of earn what you kind of earn throughout the semester. Now, if you're right on the border or something like that, I'll be happy to bump you up if you've been turning in all these things and stuff like that. But college level stuff means college level rigor. So hopefully you got everything done. You're welcome if I let you turn things in late at all, because that's not how things should be, and we were on the college's time schedule, so we're good on that. Okay, here we go. Let's talk about the new stuff. So it's not about differential equations. It's purely just another way to graph things. And you might recognize some of these things over here. If you divide both sides by r, cosine theta is x over r. That is our algebra 2 definition of what cosine is. And same thing for the y's. If you divide by r on both sides, then sine of theta is y over r. That's another thing we use from algebra 2 to define and generalize angles, the trig functions of any angle right there. Now, what this is saying is that if you're on a circle, okay, if you're on a circle somewhere and you're in an xy coordinate on the circle, like your unit circle used to be, then there's two ways to write where you are on a circle. Number one, you are in a plane, okay? You are stuck in a plane. This is two-dimensional. You need two pieces of information in order to tell me where I am in a two-dimensional structure. Traditionally, we do x and y, right? X over this way, y up that way, you know, x comma y. And that's what you've been doing most of your life, and there's nothing wrong with that. This is totally valid. But there's another way. You could do r and theta. Remember, this point is on some kind of circle. That circle right here is at a certain radius. It has a certain radius, a certain distance away from the origin. But just because you're a certain distance away doesn't mean that that defines everything. It defines a circle, a circumference. But where am I on this circle of a given radius? Well, if you tell me also the angle I'm associated with it, then I can tell you that exact same coordinate. So I can write things in terms of x's and y's as a coordinate, or in polar, I can give things in terms of r's and thetas. So I still have two pieces of information I'm giving you, tell you we're at a two-dimensional plane, but there's no reason I have to do x's and y's. I could do r's and thetas, and that would work out equally well. Now, from Pythagorean theorem right here, and I remember this from algebra 2 as well, if this is x and this is y, then x squared plus y squared equals r squared, and r would be the square root of x squared plus y squared. And if this side is y and this side is x, then that angle right there would be the tan inverse of y over x. So that's how you would find an angle. So here is what you do to go back and forth between coordinate systems. It's these first four equations. Don't write the thing on the bottom yet. I'll talk about that in a minute. If you have something in polar and they give you something at a certain radius at a certain angle, theta, then all you got to do to convert it back to good old rectangular xy is you plug in these two equations right here. Take r times the cosine of theta, that'll tell you the x coordinate. Take r times the sine of theta, that will give you the y coordinate. And so that's how you go from polar to rectangular. You want to go from rectangular to polar, that's when you use these two right here. If you have an x and a y, you can use the Pythagorean theorem, this equation right here, to get r. And you can do a tan inverse of y over x to get theta. I do want to caution you about using tan inverse. Tan inverse only will give you something out between -90 and 90 degrees. Actually, we're in calculus. Let's talk radians. It'll only give you at an angle between -pi/2 and pi/2. You might need to add on a pi or subtract a pi. Use common sense. You know, if that angle looks like it's not correct or what they gave you, then try to add on a pi or subtract a pi and see if that angle is more plausible. Because tan is not 1-to-1 over 0 to 2 pi. It doesn't pass both tests. 0 to 2 pi. It does on 0 to pi, but not on 0 to 2 pi. It's just complicated stuff like that. Now, if you, instead of graphing things like y as a function of x, it's more traditional to graph things like r as a function of theta in polar. So if your radius depends on your angle, you can get all kinds of funky looking graphs like this one or this one. I forget the names of them. They're not that important. This is a lemicon. It's like a, I don't even know what it's called. Like leaf thing, I don't know, flowers, petal, I think it's petals, I don't know. But the point is that you can graph things that look like this, where the radius is how far away you are from the origin. Don't forget that. Depends on the angle theta. So, for example, this one right here, I guess r of 0 was 1. The radius at angle 0, and remember, we're still doing this from standard position. So, starting from the positive x-axis, that is angle 0. At that angle, r must have been 1 because the distance away is 1. And then as theta goes and you go around, going around this thing from 0 to 2 pi, as you do that, the radius is going to change. If the radius becomes negative, it goes the other way, wraps back around, curls back around, things like that. And that's what it does as theta goes from 0 to 2 pi all the way around. And this one, a more kind of cute little thing, maybe it wraps around and then maybe it curls back around and curls around again, curls back around again, and does it all over. So you can get all kinds of weird looking graphs with polar that you would never be able to ascertain with just good old rectangular coordinates. But these are the conversion between the two. You got a r and a theta, got polar, plug them into these two equations, boom, we got back to rectangular. You got rectangular x and y, boom, plug them into these two equations, you got r and theta, and you might need to adjust theta by adding or subtracting like a pi or something. Now down here, you're not going to need this for this lesson, but I would encourage you to kind of tattoo it away in your brain. Because as soon as you get to Calc 3 and you start doing this all in 3D, little areas, a little chunk of area is, well, in rectangular, if you think of this on like an infinitely small little level, what's the area of this little box? It's dx times dy. And in polar, it's a little bit more complicated, but a little chunk of areas are dr d theta. And that's something that if you're going on and doing anything technical, you will need to know and you will remember eventually. But that's for more when you calculus stuff up in the future. For right now, we're just going to do the good old algebra 2 pre-calc kind of understanding of polar in general. Okay. So like I said, instead of writing x, y coordinates, you could write r theta, and that is called polar coordinates right there. And again, all those conversions I already went through and talked about right there. So let's practice some of them. Plot the points with the indicated polar coordinates and determine the corresponding rectangular coordinates. Now, these are all polar, apparently. So remember they tell you r and theta. So this one's telling me r is 2 and theta is 0. R is 3 and theta is pi over 2, etc., etc., etc. And we need to plot them. So let's just try to do them intuitively. 2, 0 means radius is 2, angle is 0. Angle of 0 means that we're on the x-axis, positive x-axis. So I'm on this positive x-axis because I haven't rotated it because the angle's 0. And the radius, the distance I am away from the center is 2. So I'm right here at 2, 0. So 2, 0 in radians is the same as 2, 0 in rectangular. That's kind of weird. Okay, what about part B? Well, part B is 3 pi over 2. So the angle, I always kind of look at the angle first myself. It's pi over 2. Pi over 2 would be up here, okay, along the positive y-axis somewhere. And the radius is 3, so I'm 3 away from it. So right here would be the coordinate 3 pi over 2 in polar. In a rectangular, that'd be the good old coordinate 0, 3, wouldn't it? Yeah, makes sense. And then C is saying negative 3 pi over 2. Now, what's the difference here? The angle is still pi over 2, so I should still be up here. When you have a negative radius, basically you flip it across the origin. So if this is where it is for 3 pi over 2, then a radius of negative 3 pi over 2 would be the exact same point, but flipped across the origin down here. So this would be negative 3 pi over 2. So what do you do when you have a negative radius, basically? If r turns out to be negative, how could a radius be negative, first of all? Well, it can't be. But in these contexts, when you're saying r is a function of theta, and theta, that function might go negative, all that means is that you are not going this way from the origin, you're going the other way. So radiuses are always positive, but if you get a negative out, that means do it like it was positive and flip it across the origin. That's what's important right there. Now down here, what about 2 pi? Well, again, this is r theta, so theta is pi. I always start the theta. Pi would be 180, so we're down here on the negative x-axis right there. And the radius is 2, so I'm 2 away from the origin on this axis, so 0's here, 2 over be right there. That would be the coordinate in good old rectangular, negative 2, comma, 0, right? So there you go. And if you weren't sure how to do that, you could go back and use the conversion equations I gave you and just plug them in. But for these, they're pretty straightforward. I think geometrically understanding what they're saying is a good idea. Now, converting a rectangular to a polar coordinate, we're going to go the other way. Find a polar coordinate representation of 1, 1. So this is good old XY stuff. Well, you could use those equations I gave you. If you got XY, you need R and theta. So R be the square root of 1 squared plus 1 squared is Pythagorean, then we're just square root of 2. Now, where is 1, 1? Isn't that 1 over and 1 up, which would just make a nice little 45-degree angle right there? So that angle is going to be 45 degrees. But of course, we're in calculus, so you want to use radians pi over 4. So square root of 2 pi over 4 would be an equivalent expression. Or, what's another way you could write it? You could make the radius negative if you wanted to. You could call it negative square root of 2. But remember what happens when you make your radius negative? That flips it across the origin. And that basically causes you, whenever you take anything and flip it across the origin, essentially all you're doing is rotating 180 degrees. So if you added on pi to what you already had, you can flip this across the origin as long as you also kind of flip this by adding 180 to it. And 180 is pi, pi over 4 plus pi is 5 pi over 4. So you could also call it this. Avoid negative radiuses if you can, just so you know if they come up, then just basically flip it across the origin. That's it. All right, so these two are actually oddly equivalent. I flipped this one by making it negative, but I also flipped this one by adding on pi and rotating it 180. So two flips kind of cancel each other out right there. All right, and they also put 2 pi k kind of stuff in there. There's really no need for that. Don't worry about that. That's stupid. Okay, then here's their equations for you, and they gave them to you, the same ones I gave you. Notice they didn't say flat out theta is tan inverse. They say tan of theta is y over x, because they're being a little more careful about that, because again, tan inverse is only defined from there to there. So really think about what quadrant you're in and what the angle should look like. And if you do the tan inverse and you get the wrong thing, well, kind of like we just said, flipping across the origin is adding or subtracting pi to something. Well, same thing. The same thing here. Then if you get the wrong answer out, just add or subtract pi. Okay. Find all the polar coordinates for the rectangular point 2, 3. So 2, 3 is x comma y. So the first thing I need to do is get r. Okay, I need r and theta. So r squared is x squared plus y squared. That's the Pythagorean theorem, or r is the square root of x squared plus y squared. 2 squared plus 3 squared is 13. So r must be plus or minus the square root of 13. In practice, again, I would kind of just say r is positive. If they give you a choice, just make r positive, make your life easy. So we also have the tan of theta is y over x, so that would be 3 over 2. So we know that tan is a positive number. Now, let's think about that. They're both y and x are positive, so I should be in quadrant 1, and doing a tan inverse is completely safe because they're both positive and things like that. So basically, I'm going to use r is square root of 13, the positive version, like I said, and just the tan inverse of 3/2 for the angle right there. And we'd leave it like that because tan inverse of 3/2 ain't pretty. On the other hand, again, did you have to choose the positive radius? No. You could have chosen the negative radius, but then you'd also have to add a pi to your tan. So be careful with your tan inverse right there. I don't think a lot of problems are going to be that complicated where you have to worry that much. Plus, I'm going to go easy on the grading on this one. I'm probably not going to grade one with a negative radius, but you never know. I honestly don't remember what I'm grading, so there you go. Now, let's go the other way again. More practice. Find the rectangular coordinate for the polar point, 3 pi over 6. So here they're saying the radius is 3 and the angle is pi over 6. So just using that equation I gave you before, x is r cosine theta. You plug it in, you get exactly 3 radical 3 over 2. For y, it's r sine theta. So you plug in r 3 times the sine of pi over 6, and that just turns into 3/2. So the rectangular coordinates x comma y would be 3 radical 3 over 2, comma 3/2. Nothing too bad like that. Now, let's start talking about graphs. Those are just points, okay? What's a graph of r equal to, and that's it, look like? Just like I could say, what's a graph of x equals 7 look like, or y equals 3 look like? You could graph those, even though they don't have both variables involved. And for part B, what's a graph of theta equals pi over 3 look like? So what happens if you just graph one of them being a constant? Well, let's start with part A. If the radius is 2, all that means is I'm a circle with a radius of 2. So here's what this one graph would look like. It's just a radius of 2 everywhere. That's all that means. That all these points here, this entire circle, would be the graph of polar r equals 2. What would a graph of the next one be? I believe it was theta equals pi over 3. That means, well, before I even go to the next slide and look, because I don't want to cheat, pi over 3, I don't know, what is that, 60? So that's like an angle like this. But how far away should I be? Well, they don't specify the radius on the second one. So it could be any distance away from it. So in fact, this is what a graph of pi over 3 looks like. It could have any r, a positive r going off forever, any positive r. You could have negative r's, and that would go the opposite way. So pi over 3 looks like a straight line, actually, which is makes kind of sense. Okay, now how about this one? Ooh, stepping it up. Find the polar equations corresponding to this hyperbola. It's got x's and y's and stuff. How in the world am I going to write a polar equation for this in terms of r's and thetas? Well, it's really easy. You know what x is in terms of r's and thetas. It's one of your slides said x is r cosine theta. So guess what you're going to plug in for r? That's right. Or excuse me, for x, you're going to plug in r cosine theta. One of our slides said that y is r sine theta. So guess what we're going to plug in for y? R sine theta. And when you do, you plug in x is r cosine theta, and you square it. R squared cosine squared would be what you get. Minus y squared, which is r squared sine squared theta. And if you want to factor out the r squared, you can. If you want to get all fancy, you can put these together. This is one of your double angle identities from cosine. Cosine of 2 theta is cosine squared minus sine squared. So if you saw cosine squared minus sine squared, you can write cosine of 2 theta. And the goal, again, just like we like y as a function of x, it'd be really nice to find out what r is as a function of theta. So could we solve for r in this case? Well, you could divide by the cosine of 2 theta. And you have r squared then is r over cosine of 2 theta. Of course, divided by cosine is the same as secant. So this is 9 secant of 2 theta. And since that's r squared, we could take a square root and do a plus or minus. Square root of 9 is 3. Square root of secant 2 theta is just square root of secant 2 theta, which is gross. And now they're getting to some domain restrictions. I'm not going to be that picky on you guys. Don't even worry about what theta could range between or something like that. You could probably think about y from this case, because what happens at pi over 4? Well, you'd have secant of 2 times pi over 4. That's secant of pi over 2. That's 1 over cosine of pi over 2. And what happens to cosine of pi over 2? It's 0, and 1 over 0 is infinity. So this thing completely blows up here and goes infinitely far. The radius goes infinitely far away distance-wise at pi over 4, and same thing for negative pi over 4, which is why this restriction is here. I don't think your homework asks you to find any restrictions. Now, these next ones I'm going to zoom through. Okay, they're not that crucial. Honestly, I've never seen them used anywhere for any reason. They're more like subtle, cute little things about polar graphs. You know, oh, by the way, what if I write this kind of format for r in terms of theta? What if I do this one kind of r in terms of theta and things like that? And they make cute little graphs, and I guess they're worth previewing really quickly. But overall, they're not that important going forward. You're probably never going to say, oh, I need to go graph a limicon, and oh shoot, have you graphed your cardioids yet? And what about that rose curve? These are not going to happen, but they're cute little things, so we should investigate them. A limicon is basically something of this format, where r is some constant plus or minus some other constant times sine or times cosines for some constants a and b. And if a and b happen to be the same number, then a special case of a limicon is called a cardioid. So like all squares or rectangles are all cardioids. Yeah, cardioids are limicons. Weird words here. Now you have also something called a rose curve. They are something where they look like r is just flat out sine of some number times theta, or cosine of some number times theta for integers a and b that are more than 1 specifically. So let's go through some. Sketch the graph of a polar coordinate 3 plus 2 cosine, which would be a limicon. Limicon, something like a number plus a number times sine or cosine. And how do you actually graph these by hand? Well, let's see. First, here's what they're going to do in there. I don't like to do this. Let's just the heck with this. Let's just go for it. Okay, here's the whole shape right here. Ready? And I really wish I had a copy of the equation right here. 3 plus 2 cosine. Keep that in mind. This is 3 plus 2 cosine theta. So what happens when theta is 0? Well, we got 3 plus 2 cosine of 0. Cosine of 0 is 1. 3 plus 2 would be 5. So my radius is 5. So at angle 0, I am 5 away, and it starts right here. How do you pick points to check where you're at? Pick some common angles. Maybe try pi over 4 next. So let's go back to our equation. What happens at pi over 4? Well, they already got it all put out here for us, but at pi over 4, cosine of pi over 4 is square root of 2 over 2. 2 times square root of 2 over 2 is just square root of 2. So my radius is 3 plus square root of 2. Square root of 2 is about 1.414, so 3 plus that would be about 4.414, so about 4.4 or so away. Now that means at an angle of pi over 4, which is this angle right here, I should be about 4.4 away or something like that. So if you start here and you go out at a pi over 4 angle, about 4.4, you'd land about here. So now I know this point is here and that point is there. Great. Well, let's try another common angle. How about pi over 2? So what happens when you plug pi over 2 into this equation? Well, cosine of pi over 2 is 0. So 2 times 0 is 0, and 3 plus 0 is 3. So my radius should be 3. So at an angle of pi over 2, which would be up here, right, along the positive y-axis, I am 3 away. So right there is the point 3. And you just painstakingly, this is how you graph polar equations. And by the way, your calculator does graph polar equations. So go to mode, and it's one of those things we haven't used. The first thing it says function, and it's got param for parametrics, which we've done. It also says POL for polar. So if you're being polar, and make sure you're in radians for this stuff, you can go just plug this in your calculator and it will go do this whole thing for you. But if you wanted to graph it by hand, this is how you would do it. You would pick an angle, you would plug it into the equation, you would figure out what R is, and you'd go back to that angle and you'd go that distance away at that angle and plot a point. And you would painstakingly do this for various angles all the way from 0 to 2 pi all the way around, and you would slowly get a picture of what this thing looks like. Over here, you'd probably see some weird things. It'd be like a pi over 4, and be probably farther away than this thing right here. But this is what a limicon looks like in the end. It's kind of like a circle, but one side's kind of bashed in or something like that. All right, now this is a cardioid, and now what does that mean? It's the same thing as a limicon. It's just that these two numbers happen to be the exact same thing. So it's 2 and 2. So again, we could painstakingly go 2 minus 2 sine. So let's see what that would be. When theta is 0, so we're kind of along the positive x-axis, 2 minus 2 sine. Sine of 0 is 0. So it would be 2 minus 2 times 0, 2 minus 2. So I'd start right here at this point, 2. And then again, as you rotate this way at different angles, you have different radiuses away. And apparently, right here at pi over 2, we're at the origin. That radius is 0. Let's see if that makes sense. At pi over 2, what do you get? The radius should be 0. Let's see. Pi over 2 is, sine of pi over 2 is 1. So I have 2 minus 2, which is 0. So right there, it kind of bounces, it does a little bounce right there and goes out like this and kind of repeats. And again, if you were going to do this by hand, you would painstakingly pick different angles and plot their radiuses. I'm at, you know, 5 pi over 4 or something like that. Well, I'm kind of like right here, so I plug in 5 pi over 4. And the radius would be whatever it is, and I go that far away, and I plug a point, and then pick another angle, and figure out what the radius is, and plot that point. And it's just very tedious to do this by hand. You probably definitely want to use your TI-80 whatever's for graphing polar, because doing it by hand is just a painstaking process. It's like trying to graph a inverse tangent function when you're in algebra 1, and all you know is I can plug in x's, and it hits them in a calculator. It gives me a y, and I go plot the point. You have no feel for what this is going to be. What's the main difference between these two, by the way? Here is a limicon, okay? So it goes all the way around, and then it kind of has this little indenture here, but this indenture doesn't come close to the origin. But when they're the exact same number for a cardioid, then it turns out that it actually does have that little bump in it, but that bump actually is like a little corner, and then it comes back outside like this. So there's another graph for you. Again, you're never going to use these terms again, probably, but cute little graphs, and you should investigate. You should actually put them in your calculator and graph it, make sure you can get these graphs, and make sure you're in radians and all that stuff. If you're in polar, then the first thing it says in polar is like R equals blank, and you plug in a bunch of things with thetas in them. And where's your theta button? It's the same as your X button. It's the same as your T button for parametrics. It's the X button. So you hit that, and if you're in polar mode, it'll know to graph that. Okay, this is a limicon with a loop. Let's take a look at this thing. 1 minus 2 sine theta. Now notice that this time the thing in front of the sine is more than this number right here. So we would go through the same kind of logic. We would go angle at a time. Here's the first little bit. It traces out this. Then it kind of, at further angles it does this. And, as the angles go around, it might loop around once or twice or something like this. And here's a limicon with a loop. So that's a cute little graph. Here's a four-leaf rose. Now, that's the term I couldn't think of in the warm-up. You might wonder why this is called a rose. First of all, what is a rose? It's something of the form sine of some number more than 1 times theta, or cosine of some number more than 1 times theta. But if you graph this, it's called a rose because it looks like a rose. As you slowly plot things out, you get petals to it. How many petals there are is kind of dependent on, you know, some number theory things about the numbers involved in this stuff, but you would get something like this. And then I'm not going to go through the details again of how you would painstakingly plot this point by point by point, but essentially at angle 0, you would be having a radius of 0, so you'd be right there at the origin. At angle pi over 4, your radius would be this, so you'd be at this point right here, so you kind of start here and move out. Then at angle pi over 2, your radius would be back to 0, so it kind of closes in on itself. And you just keep going around and around and around at different angles, and eventually get this thing. Do not graph these by hand. Okay, if they ask you to plot a point, fine. But if it's going to make you graph an entire thing, these are too complicated, and we're too green at it to just know what it's going to look like. So let your calculator do the work for you. And that's kind of all there is to polar right there. So let's do a quick one from your homework, and that'll conclude this lesson. I'm going to do number 51 for you. It says, find a polar equation corresponding to the given rectangular equation. Okay, so here's this kind of hyperbola given to you again. And this isn't rectangular, it's x's and y's. How do you get from, well, what's the conversion between the two systems? Well, first thing first, x can be written in terms of r and theta by r cosine theta. Y can be written in terms of r's and thetas by r sine theta. So if you substitute those in, you get r sine squared minus r cosine squared, both as quantity equals 4. This is kind of like one that they had in the examples earlier in the homework, or in the lesson. But if you square all this thing, you get r squared, and then there's an r squared in both of these. You can factor it out, and what will be left is a sine squared minus cosine squared, which if you divide it on both sides, because remember, you're trying to get r as a function of theta. That's your goal. It's like, you're like, why as a function of x? You would like to have r as a function of theta. So you're trying to get r by itself. So if you do this, you get r squared as 4 over sine squared minus cosine squared. Now, I see sine squared minus cosine squared. I'm thinking double angle identity, but it's not quite in the right format. Double angle identities for cosine are cosine squared minus sine squared, not sine squared minus cosine squared. Easy fix. Multiply the top and bottom by a negative, and you got -4 now over cosine squared minus sine squared. And let's see what happens there. On the bottom, cosine squared minus sine squared is the double angle identity for cosine, so that's just cosine of 2 theta. And this all just turns into -4 secant of 2 theta. And how do you solve for r from there? Take a square root. I'm going to leave it positive. You can choose 2 different ones, but you know, it doesn't matter which one you do. There's some restrictions on your angles and things like that, but it'll graph both of them if you restrict things. And square root of 4 is 2. Now I got a negative under the root, which might be scary, but that's okay as long as the secant thing itself is negative. So r is given by 2 square root of this in this case. Okay, now let's think about this real quick. This is a fine answer, and this is what's in the back of the book. But I'm going to go a step further, and I'm going to model how would you actually figure out the angles involved. So like I just said, when we solve for r, we need this stuff under the root to be positive. And since there's a negative under there already, I need secant to be negative. Now, what is secant? Secant's 1 over cosine, right? Where is cosine negative? Cosine is negative between, let's see what angles. From pi over 2, think about that. Think about your cosine graph. From pi over 2 all the way to 3 pi over 2, that is where cosine is negative, and hence when secant is negative. And I'm going to be a good little pre-calc student, and I'm solving equations where the angle 2 theta is between pi over 2 and 3 pi over 2, but since I got that 2 theta, I better slap on some 2 pi k's or something like that. So I'm going to do some 2 pi m's, mix it up. So as long as 2 theta is by pi over 2 plus 2 pi m or anything coterminal to it, or 3 pi over 2 plus 2 pi m, anything coterminal to that, but as long as between those two things, then secant, the secant will be negative, and a negative times a negative is going to be positive, and things can be fine. Okay? And the reason I didn't include those, actually, have less than or equal to, or greater than or equal to, is because I can't actually have secant equal, I can't actually have cosine be 0, because then secant would be undefined, it'd be an asymptote there, and this function would also not be defined. But just like in pre-calc, how would I solve this from here? I got 2 theta, so I'm going to divide out both sides by 2. Dividing pi over 2 by 2 would be pi over 4 plus pi m. Okay, the 2 pi got divided by 2 also. And over here, the 3 pi over 2 plus 2 pi m divided by 2 would be 3 pi over 4 plus pi m. And now I know what theta has to range between. Remember, m is an integer. If m is 0, then I guess theta has to be between pi over 4 and 3 pi over 4. Cool, nice. And if I add on, well, with m is 1, well, if m is 1, then this is pi, and this is going to turn into 5 pi over 4. And on this side, if m is 1, then 3 pi over 4 plus pi is going to be 7 pi over 4. So there's 2 different angles I need to consider where this is defined. Between pi over 4 and 3 pi over 4, and between 5 pi over 4 and 7 pi over 4. So if you go to your polar equation graph, go to y equals now, make sure your mode is switched, it should look just like this. And type in what r is. R is 2 times the square root of secant, or negative secant, so negative 1 over cosine of 2 theta. Your theta button's right where your x button is. And if you go to your window, you got to be careful how you do this with the window thing. If once you make your window from pi over 4 to 3 pi over 4, it'll graph one branch of this parabola. And if you make it from 5 pi over 4 to 7 pi over 4, it'll graph this other branch of the so I shouldn't say parabola, sorry, hyperbola. Both branches, one branch and the other branch, are going to be graphed, one by this set here, this by this other set here, and their union would represent the entire graph of this thing. Now you can't have it be any angles in between them, because then this radius becomes imaginary. It doesn't make any sense. You could probably just plug it in like this and not even worry about this with your window, because what's going to happen if it tries to graph something imaginary? It's just not going to graph it. So it just won't graph things at angles that don't make any sense. You don't have to put this restriction on it like there, and your graph will work. I do warn you though, like graphing any hyperbola, that if you try to graph it all at once, it might graph it one way, and then it might jump back and have that, slant line that's not really there. It's possible. So just watch out for that. But that's it. Okay, so there's number 51 for you. There's the answer. It's gross, but it is correct. R equals 2 times the square root of negative secant 2 theta. I was even doubting myself when I did it. I'm like, boy, that's a weird, funky looking answer. I even got the teacher manual out, and I looked at the answer key just to make sure, and I was right. I just doubting myself. You might get some weird R's out in terms of thetas. That's it. All righty, guys, and that kind of concludes the lesson. So, like, again, you have your extra credit due tomorrow. Get that turned in if you want 10 points extra credit for completing those, or however many are right. I'll give you a fraction of the extra credit it's worth, depending on what fraction is correct. Your notebook check, again, freebie, you're welcome, 50 out of 50. Last semester you got to have it because of a snow week or something like that, and this semester you got to have it because of COVID. So Mother Nature does not want you guys to have your notebooks checked off with you for some reason. And your homework over Polar is 9.1. It is page 666. Ooh, ominous. 3 through 63 multiples of 3. So half of them will be odd, half of them will be even. And then you can pretty much, kind of check your answers on some of them, make sure you're doing them right, and then you can have a little more confidence for the even ones there. That'll be due on Thursday, and again, as long as everything's turned in by the end of the week on Friday, I am happy. And guys, that concludes Wellsville High School's Calculus 1 and 2 course. Now, you're only getting college credit for Calculus 1 on this stuff, but a lot of things we've touched on are in Calculus 1 and 2. So if you take both courses, neither one of them will throw anything brand new at you that's going to blow your mind. We've covered everything. Calc 2 might go far more in depth with polar and parametrics, maybe even. It might go a lot more in depth with Taylor series and differential equations and things we just touched on the last week or two in this class. And maybe the algebra, they might put you through more of a ringer and give you far more algebraically ugly kind of things to deal with. But the theory of calculus at the bottom level, you guys have been exposed to everything, and your integration techniques, you know them all. You know everything about how to take derivatives. You know pretty much all the applications of these kind of things too. The volumes and surfaces of revolution and work and physics, and back in semester 1, with mins and maxes and concave up and concave down and related rates and everything you could possibly do with these things. So you guys have a very well a good strong grasp of basic calculus now. So you are welcome to go on to the next course, Calc 2. You should feel confident trying that. Jumping right to Calc 3 right now, you could do that too if you got all these things down. You could figure it out. And Calc 3 is really not anything more difficult mechanically than this. It's a lot more rules, applying things to vectors and things like that. So there are some new terms and there are some new things conceptually to understand what's going on in 3 dimensions. But actually working out the problems, it's just taking derivatives and integrals, just like you already know how to do. It's just doing them in new ways that you're not comfortable with yet. So that's it. I hope you guys do go on. You're all very smart kids. And as parting words for any of you that are going on and will not be back next year, seniors and all that, it's been a pleasure to teach you guys. I tease you guys a lot, but it has really been reward. My job is so frustrating sometimes. I just want to beat the crap out of kids. But the most rewarding thing I do is I see you guys come in Algebra 2, and you're smart kids. All the kids in my calc class are always smart kids. You're all very smart, but you come in and you kind of got some deficiencies, and you're kind of weak, and your algebra is very unclean. And to see you in Algebra 2 grow and get all those kind of basics down, and then in pre-calc get them all cleaned up and ready to go, and then go through calculus and really have a strong command of all your algebra and your pre-calc and your calculus, it is so rewarding over the years to see you guys progress and get so much better. So I am honored to have been your teacher. I hope you found it enjoyable for me as well. Please go on and do more mathematical things. Have a good life. Keep working hard. Do something technical or something that's going to trip your trigger. Do something that's going to make you happy. Marry somebody nice. Be a good person too, because you got to live with yourself. If you're always comfortable with who you are because you're a good person, you got good morals, and you treat people nice, and you're smart, and you know things, and you learn, and you can continue to have your pursuit of knowledge, and you find love, and you'll all find love with somebody, make sure they're a good person. Screen them real carefully. Don't just run into anything. And don't do that first. Oh, I'm young and I love them. No. Wait a long time. Wait till you're like 25 at least to get married or anything like that. Don't do anything rash, please. I beg you. But I look forward to seeing you guys grow. And I want you guys to come back and at least shoot me an email or talk to me someday and let me know how life is going. Because I do care about you guys on a genuine level. And I want to see the best for you. That's why I work so hard. That's why I get frustrated, just like any parent would if their kids are doing something they're not supposed to do, or they're doing something not good for themselves. You get frustrated because you care and you want what's best for them and you want to see them succeed. And I want to see you guys succeed too. And I think you will. So just keep up being who you are. You're all good kids. You're all smart kids. Good luck in the future. And I love you guys. I love you guys. I'm going to miss you guys. So hopefully you'll stop by and have a proper goodbye sometime. But please keep me posted. I know you go off and live your adult lives and you forget all about your high school math teacher. I get that. But, please stay and come back at least once or twice before you disappear into the world. And let me know how college is going. Let me know how your lives are going. I do care about you guys. So keep up the good work in life. Just keep doing what you did in this class and have that work ethic everywhere and have that good attitude and that good respect. And you guys will go as far as you want to go. So love you guys. Take care. And again, everything is due by the end of the week. So get that all taken care of. Extra credits due tomorrow, though. So get that taken care of as well. And that concludes the course. It's been an honor being your teacher, guys. I will miss you all. Take care and good luck in the future.